Ian Agol, who will talk about virtually special cube complexes.
All right, thanks, Joe. All right, thanks to the organizers for the invitation to speak. And so today I'm going to talk about virtually special cube complexes. In particular, I want to discuss some results of Dani Wise and his collaborators that, well, he's talked pretty extensively about, but I guess my collaborators, Daniel Rose and Jason Manning, together were sort of reworking some of his arguments in a kind of different, using slightly different technology, getting sort of more geometric proofs of some of his work. And, but really just sort of reorganizing the material. I wouldn't say we have that many sort of new insights or ideas, maybe a few simplifications, but not really, nothing, I mean, it's really following his approach. So that's kind of what I wanted to give some idea of today. And I think a lot of people here are aware that, you know, this is sort of the work that was underlying my work on the virtual Hawking conjecture, but I've been talking now about the virtual Hawking conjecture for a year and a half or so, and I think, looking at the list of speakers anyways, I think most people in this room have heard me speak at least once about this, so I didn't really want to talk about that again, which is why I'm talking about sort of really older work of Dani Wise, but maybe from a slightly different perspective. Okay, so so if you're hoping to hear about three manifolds today, there might sort of not really be much, but more just lurking in the background. Okay, so the main things I want to talk about today are topic will be a combination theorem of Hsu-Wise and the Malnormal special quotient theorem of Wise. So this second theorem is sort of the key, or it's with its statement, it's sort of the key thing that I need in my paper and in the appendix with Groves and Manning that's powerful enough to sort of imply what we need. But this theorem is proved in sort of a bootstrapping way where so Wise was interested in the Malnormal special quotient theorem for proving his theorem that if you have a hyperbolic group with a quasi-convex hierarchy, then it's virtually special. In particular, it's linear and residually finite, has certain subgroup separability properties and things. But in order to prove this theorem, he uses sort of a weaker result of the result he wants to prove, namely, he proves that if you have a hyperbolic group which has a malnormal quasi-convex hierarchy, then it's virtually special, and that makes use of this combination theorem of Hsu and Wise together with the result of Agol and Wise, which has appeared recently in the Annals of Math, and so it's sort of this intricate inductive argument that he has set up. So I want to describe, anyway, some of the ingredients that go into this. So that's, so I need to explain, first of all, what are these topics. So cube complexes, well, they're complexes made of, by gluing cubes together, and they're glued along faces. So we take a bunch of cubes and we glue them together along lower dimensional cubes. And a cube complex is non-positively curved, if it satisfies Gromow's flag condition. So a cube complex is non-positively curved if its universal cover is cat 0, so it satisfies a comparison inequality with Euclidean triangles of the corresponding size, but the geometric version of that is not sort of directly relevant to the sort of arguments. So the more directly relevant thing is Gromow's flag condition. So if we had a cube complex that looked like this, say we glue 3 squares together, maybe something like this, then if I look at a vertex, we can look at the length of the vertex. So I'm assuming here that these are all squares. And at the length of this vertex here, so the length is attained by taking a little epsilon neighborhood around the point and intersecting the sphere with all the cubes that meet that vertex. So then you get a simplicial complex that sort of chops off the corners of the cubes. And here what we see is an edge of an isolated vertex and then a triangle. So the flag condition says that for every clique, so complete graph in the link of the vertex, there has to be a simplex that fills that in. Well, if there's a simplex that fills in this triangle here, then that has to be filled in by a cube. So that means that there's actually a cube that sits here, a 3-dimensional cube that fills in that corner. So the length of the vertex then satisfies the flag condition. That implies that there's actually a simplex. So if you take any simplicial graph, there's a canonical simplicial complex that you get by taking every n click and filling in an n-1 simplex into there. So that's a flag complex. So Gromow's flag condition says that the lengths of the vertices are flag complexes.
Are they locally finite or no?
No, they don't have to be locally finite. Yeah. Okay, so, but I'll be interested in locally finite ones pretty much in this talk. Okay, so then a hyperbolic group, just to quickly review. Oh, maybe before I do that, I should discuss hyperplanes. So when you have a simply connected non-positively curved cube complex, or well, sorry, any non-positively curved cube complex, then there's canonical immersed hyperplanes. So in each cube, I can take a, if it's an n cube, I can take an n, there's n-1 cube. So here's a 2 cube, there's 2 codimension 1 cubes. So you can stick in each of these cubes in an edge. There'll be a single codimension 1 vertex. In a 3 cube, you'll see 3 squares that cut it in half. So we can take these and we can, when 2 cubes are glued together, there's a canonical way to glue the corresponding hyperplane. So this hyperplane can be extended into here, and we get 3 of these in a given cube. Now, if it's a simply connected non-positively curved complex, it's globally cat 0. These hyperplanes, it turns out, will be embedded. They can't come back and intersect themselves. You'll violate the cat 0 condition, it turns out. But if it's locally non-positively curved, but the fundamental group's non-trivial, these hyperplanes can come back and self-intersect. But we want to think of the 2 sheets coming in as being separate, as being an immersion of a complex that's mapped in. So what's kind of nice about these cube complexes, they behave a lot like manifolds in the sense that these hyperplanes sort of they intersect transversely to each other. They have a sort of a product structure, or when several of them meet, they'll look like the corners of a manifold because you're just intersecting inside of a cube. And that's quite useful for some of the arguments that you can make with these cube complexes. They behave very analogous to codimension 1 surfaces and manifolds. Okay, so now, these are hyperplanes. And the CAD0 condition also implies that these are CAD0 cube complexes that are locally isometrically immersed. In particular, they're pi1 injective, which is also sort of key for the kind of arguments that are made. Okay, so a hyperbolic group is finally generated. Has some generators, and well, there'll be some relations, but I'll ignore that. So we can take the Cayley graph of G. So let's say it's subset S with respect to the set S. And this should be a delta hyperbolic metric space for some delta. So what's the delta hyperbolic metric space? So the metric on the Cayley graph is the edges are, say you have length 1, and then you take the minimum number of edges of a path connecting 2 points. So it's delta hyperbolic. There's a couple of different versions of this, but if you have any 3 points, A, B, and C, and you take geodesics connecting them, then the point is that the geodesic connecting B and C will be contained in the delta hyperbolic neighborhood, and I'm going to make sure I don't screw this up. So if you take the delta neighborhood around the geodesic connecting A and B and the geodesic connecting A and C, then it contains the geodesic connecting B and C. So the geodesic that connects B and C sort of tracks the geodesic connecting A and B for a while, and then skips over and tracks the geodesic connecting A and C. So an example of a delta hyperbolic metric space is HN, hyperbolic n space. I think it's log of 1 plus root 2 hyperbolic or something. Turns out that well, stability of quasi-geodesics implies that if you have a hyperbolic group, then you choose a different generating set. It'll be delta hyperbolic for some potentially other delta, but it'll still satisfy this delta hyperbolic condition. So if we take geodesics connecting B and C, it's contained in the delta neighborhood of the union of the other 2 geodesics. Okay, so turns out that delta hyperbolic groups, well, by definition, they're finally generated. It turns out they're always finally presented, and they have lots of other nice properties. So examples are free groups, and pi1 of M, where M is closed and negatively curved. But not, say, the pi1 of the figure 8 knot complement is an example that's not delta hyperbolic. So, oh, and I just drew the white link complex. That works too. Okay, so And in particular, inside of say a cusp hyperbolic manifold of finite volume, you'll have these z-squared subgroups, the fundamental group of these tori, and that violates. It turns out can't happen in a hyperbolic group. Any abelian subgroup has to be virtually cyclic. But delta hyperbolic groups can have torsion. There'll be finitely many conjugates classes of torsion. Okay, so now the object of study then, so definition will say that G is cubulated if at X properly co-compactly on an MPC, I'll say cat 0, sorry. Cube complex. So a non-positively curved cube complex satisfies Gromov flag condition. It's cat 0 if it's also simply connected. I mean, that's really a theorem, but it's cat 0 with respect to the metric where on each cube you make it into a Euclidean cube with, say, edge length of side 1 or 2 or whatever you like, and you glue them together by isometries. Then you can extend that to a metric like a path completion, and that's a cat 0 metric. Meaning that if you look at it, there's a kind of similar comparison to where you compare it to a Euclidean triangle, and the side of one triangle is always closer to the opposite vertex than the corresponding Euclidean triangle. So with respect to Stavros' question, if it acts properly co-compactly, well, a compact cube complex has to be finite dimensional, because if there's cubes of arbitrarily large dimension, then it'll have to be non-compact. So it's finite dimensional, but it'll also be locally finite, because again, if it's going to be a proper co-compact action, well, a compact cube complex has finitely many cubes, and you can have a graph with infinitely many edges coming into a vertex. But the action, and there'll be an action there which is co-compact, so this happens with amalgamated product splittings. But the stabilizer at this point will be non-compact, and so it won't be a proper action. So it'll have to be locally finite as well. Okay, so the main theorem that I proved last year was that if G is hyperbolic and cubulated, then oh, sorry, I forgot to define special event. Virtually special, so I need to define what a special cube complex is. So G is special if it acts on a cube, a Katzo cube complex. X, so that G mod X is special. It's a special cube complex. And a special cube complex is was introduced by Agol and Wise around 2008 or so. Oh, maybe I should have, sorry, I should have kept up that one. So in a cube complex, we can think of the hyperplanes as an equivalence relation on the edges of the cube complex. So if I have an edge, then I say it's parallel to another edge if it's on opposite sides of a square. So this is all determined by the 2 skeleton. And then so you take the relation generated by that. So if there's a sequence of squares that go between edges, then we see that they're parallel. So hyperplanes are equivalence classes of edges in the cube complex. And a hyperplane is embedded if and only if in any cube there's a unique equivalence class of edges induced from any hyperplane. So hyperplane is embedded. If and only if the equivalence relation gives an induced hyperplanes in the cube. In each n cube. And there's also, we can look at oriented edges. So we can talk about, we might have a sequence of edges which come around and come back with the opposite orientation. So we'll say that the hyperplane is co-oriented if that equivalence relation preserves the orientation of the edges, of oriented edges.
All hyperplanes are edges. It's not a condition, just one, right?
Oh, yeah, sure, yeah, all hyperplanes, yeah.
So Ian, in your definition of special, you say it acts on this cat zero cube complex. I mean, is that action proper co-compact or not?
Oh, yeah, sorry. Yeah, that's right. I mean, as a continuation of the...
Right, I just...
Yeah. It turns out that a cat zero cube complex is always special. So so now we have these equivalence relations on edges that we can talk about the special conditions. So two hyperplanes osculate if there's if you see at a vertex an edge that's like this and another edge with the same color. Here I'll assume hyperplanes are co-oriented. So we'll assume co-oriented. So we'll allow us directly self-osculating like this. So this will be okay. Oh, sorry. This will be osculating, and you can talk about. Sorry, that's for a self-osculation, I should say. Self-osculating. But we say two hyperplanes osculate if there's a vertex where they meet like that. Okay, so so a special cube complex is an MPC cube complex if it has embedded co-oriented hyperplanes. And the hyperplanes there's no self-osculation. of this sort. This is okay. So this is okay, this is not okay. Or interosculation. So what this means is that we don't see two hyperplanes here that that osculate in an edge. And sorry, I should have said by osculate here, I mean they share a vertex and there's not a square, there's no square filling it in. In other words, you don't see a picture that looks like they don't cross at a square. So you would see an osculate, I mean this is not considered to be an osculation at this vertex here because the two hyperplanes are crossing each other. So that means, so they're interosculating. If you see this picture it's in some square and you see an osculation somewhere else, then they're interosculating. So they cross somewhere and they're sort of osculating or tangent somewhere else. So this is an example of an interosculation. Okay, so a cube complex is special if it satisfies these conditions. The nice thing about special cube complexes, which again I don't really want to get too much into it today because it's not so relevant for the arguments that come into these other theorems, are not directly relevant, but what these special cube complexes, the property they have is that the fundamental groups embed into right-angled arc groups. You get a locally isometric immersion into the Salvetti complex of a right-angled arc group associated with a special cube complex. So we heard about right-angled arc groups yesterday in Joanna's talk, and I don't think she defined Salvetti complex exactly, but Salvetti complexes are sort of, right-angled arc groups are sort of the epitome of special cube complexes. In particular, their fine-sheeted covers are always special. They have embedded hyperplanes. There's no oscillations, although there is this sort of direct self-osculation, which is okay.
What about like double osculation? What if you have two guys that?
Yeah, they can doubly osculate. Yeah, yeah. So I could see. Yeah, that's fine because that's preserved. That's also going to happen. You know, if you take a fine-sheeted covering space.
Yeah.
So the point is, why is this interosculation not allowed? So what will happen is you'll get you'll have a node for every hyperplane in your complex, and you'll have an edge between two nodes of the defining right-angled arc group. If two hyperplanes cross, in the Salvetti complex, then you'll see these sort of crossing hyperplanes associated to generators of the right-angled arc group. And if they cross at some point, then they have to cross everywhere else, because otherwise this guy would be mapped into a corner in the Salvetti complex, which would not be locally isometric, or not Pilot injective. So that's sort of one of the reasons that the interosculation is not allowed. But again, I don't really want to get too much into that theory right now. Okay, so back to the content of this theorem. So if G is hyperbolic and cubulated, then G acts properly co-compactly on a Katz-O cube complex, say X. Then saying it's virtually special, so virtual means there's a finite index subgroup that satisfies that property. So in particular, G acts properly co-compactly on X, and there's a finite index subgroup, so there exists G prime in G finite index. So X mod G prime is special. Now it turns out that, well, if there's some cube complex on which it acts properly co-compactly, and there's another one on which it acts properly co-compactly and it's virtually special, then it's a consequence of the Agol-Wise theory that for any other cube complex, it'll have the same property, maybe for possibly a different finite index subgroup. So the property of being virtually special actually does not depend on the cube complex that you that G acts on. Okay, so I think that's the statements of the statement of the theorem, but I'm not going to get into the proof of this today. But I'm going through some of, as I said at the beginning, some of the background material of Dani Wise and his collaborators that's used to in a key way in the proof of this theorem. So I'll try to state the combination theorems. Now I need one more definition, quasi-convex subgroups, or quasi-convex. Again, this is in Joanna's talk, so I'll go over it pretty briefly. So a subset of a delta hyperbolic metric space. So delta hyperbolic metric space satisfies this delta hyperbolic condition, but I forgot to say that in general, delta hyperbolic space is a geodesic metric space, meaning between any 2 points there's a geodesic between them. So it's lambda quasi-convex. If for any geodesic connecting points of y is contained in a lambda neighborhood. So, for example, cyclic subgroups of a delta hyperbolic group. Well, really, I mean, cyclic subgroups, just thought of as a discrete set of points inside of the Kähler graph of a delta hyperbolic group, is a quasi-convex subset. A subgroup then is called, a subgroup of a delta hyperbolic group is called quasi-convex if it's quasi-convex inside the Kähler graph for some, if it's lambda quasi-convex for some lambda. So h less than g, g is delta hyperbolic, is quasi-convex. If h is a subset of gamma of gs is lambda quasi-convex for some lambda. And again, properties of delta hyperbolic groups imply that if you chose a different generating set, that h would still be quasi-convex, again, for potentially some different lambda. An exercise is that if I take the neighborhood of radius lambda about y, if y is lambda quasi-convex, then the neighborhood of radius lambda about y, so by this I mean you take all the points that are distance lambda from y, is 2 delta quasi-convex. So you can enlarge any quasi-convex set to a, well, so a set is convex if every geodesic is contained inside of it. The notion of quasi-convexity is sort of coarsening of that, but by taking a tubular neighborhood of it, you can guarantee that it's uniformly quasi-convex for some uniform constant, if you like. Okay, so the subgroup is called Malnormal. If it intersects all of its conjugates trivially. So it intersects its conjugates in the identity. There's also what's called almost malnormal, which would say that it intersects any non-trivial conjugate in a finite subgroup. But I'm not going to write that down right now. Okay, so the statement then of Hsu and Wise for again for let's say a maximal cyclic subgroup of a torsion-free delta hyperbolic group is always malnormal, it turns out. So you can think of like a maximal cyclic subgroup of a free group is an example of a malnormal group. So let A and B be virtually special, cubulated hyperbolic groups. Well, cubulation is part of the virtual special condition. So again, here when I say hyperbolic, I don't care what the hyperbolicity constant, just for some choice of generators, and let C be a common subgroup of A and B. So I'm going to sort of abuse notation, say C is a subgroup of A and C is a subgroup of B, whereas I really mean there's subgroups of A and B that are both isomorphic to C, but hopefully that's clear. Then and C is malnormal and quasi-convex. In A and B, then G, the group A star B amalgamated along C is cubulated. So just a remark on the history of this result, that Hsu and Wise had an older version of this for amalgamated products of free groups along cyclic subgroups, maximal cyclic subgroups. There's also an H&M version of this, but I'm going to sort of just ignore that.
Special or virtually
Graphic groups.
special?
What's that?
Amalgamated product special or virtually special?
A and B are virtually special. C is malnormal quasi-convex. Then there's a cube complex in which G acts properly co-compactly. That's the statement. And then, so the remark, an older version, by Hsu-Wise for the case A and B are free groups, which are delta hyperbolic, and C is cyclic. Or more generally, a graph of free groups along cyclic subgroups. And then I think, yeah, so that's an older version. Yeah, I think Wise then had a version for amalgamated products of free groups along malnormal, general malnormal subgroups. That was Invenciones, the Polygons of Finite Groups paper. And that paper is sort of the low-dimensional version of his more general results. So he sort of first was working in these low-dimensional cases, and then sort of gradually realized that he needed to go to higher dimensions and work with cube complexes. So he had to generalize all this technology that is much more elementary for free groups to these higher dimensional cube complexes. So a lot of these results are easier to understand in the free group case, where things are a little more explicit. And then another remark by a result of Kapovich. In this context, C is quasi-convex in G, and then by the combination theorem of Fein and Besvina-Fein, G is hyperbolic. So I could have taken that as sort of part of the input to this theorem that G is a hyperbolic group and C is actually quasi-convex inside of G. If C is malnormal in A and B, then it'll also be malnormal inside of G as well. That follows sort of from the normal forms for amalgamated products. But does everyone understand what I mean by amalgamated product of groups? So it's a push out of this diagram of groups, if you like.
So G is not a special?
Oh, so yeah, so that's the next thing then. That's right. So G might not be special, but yeah, again, A and B are only assumed to be virtually special. So this theorem applies as well to, for example, when A and B are virtually free groups. So amalgamated products of the graph of finite groups, for example. So then the theorem of Hsu-Wise. So under the same hypotheses, if G is cubulated, so then G is virtually special. So together, these two theorems imply that under these hypotheses, G is also virtually special. So this, actually, we're writing down this a little more carefully. It's not precisely how it's stated in their paper, but it's sort of an easy consequence of their result. And I forgot to mention at the beginning that this will be a joint work with Groves and Manning. Anyways, so we worked out an alternative proof of this Hsu-Wise theorem. This Hsu-Wise theorem I said appeared recently. This is sort of a lot of the heart of the proof of Wise's work, I think. This is a really sort of difficult theorem, but it harkens back though to his earlier theorem on polygons of finite groups. So generalizes the polygons of finite groups paper. Okay, then now I wanted to state though what these are used for. So then the consequence of these two theorems put together are that so amalgamated products of virtually special groups along malnormal subgroups are virtually special. And you can iterate that then. So if you have if G has if G is hyperbolic, it has a malnormal quasi-convex hierarchy, that G is virtually special. By a hierarchy, what I mean is that there's an iterated graph of groups construction where you have G as amalgamated products of two groups, which are along a malnormal quasi-convex subgroup, or it's an H&N extension along malnormal quasi-convex subgroup, and each of those groups has a similar property until you get all the way down to the terminating. So this is a hierarchy terminating in finite groups. Well, finite groups are virtually special. Because the trivial group is, and so this applies, for example, if you have, say, a hyperbolic three-manifold that has a bunch of embedded totally geodesic surfaces that chop it up into balls. Then you can show there's one of these malnormal quasi-convex hierarchies. With embedded totally geodesic surfaces. So this Malnormal hierarchy theorem then was, so Wise proved the generalization of that 2011 or so, that if you have a hyperbolic group with a quasi-convex hierarchy where the splitting groups are not necessarily Malnormal, then he proves that those groups are virtually compact special. Now, but the proof of that theorem, the more general theorem, makes use of this. So you have to sort of go through the proof of this first before understanding the general theorem. And the way that you reduce from the general case to the Malnormal case is, well, it's a little complicated, but it's via the Malnormal special quotient theorem. So I at least wanted to state that. So this was due to Wise. You know, this is page 120 or so of this 189-page document, and about 100 pages or so of that paper are Wise is developing this cubical small cancellation theory, and what we've done now is sort of replaced that technology with a different technology, which is maybe, you know, I don't know if it's any simpler. You know, but it's already in the literature, and there's various approaches to it of relatively hyperbolic filling. So, so now we have an alternative proof of this, and it's actually somewhat strong, slightly stronger than Wise's result, although we don't really have any applications of the stronger statement. So,
How many pages? How many pages? How many pages?
Wise's?
No, yours.
Oh, well, so far I think we have like a 30-page preprint, but we're still working on it, yeah, so yeah, I'm not sure. But the thing about our approach, I guess, is that I think it's a little more geometric, and it's, again, it's really following Wise's argument, but sort of rearranging the order that things are done and so much. Okay, so let G be virtually special, hyperbolic. And P a collection of I should have said a Malnormal collection of subgroups. Let me just define that. I forgot to define the more general version. If you don't like that, you can just take P to be a single Malnormal subgroup of the quasi-convex. So each of these PIs is Malnormal, and if you look at the conjugates of PI and PJ for any I not equal to J, their intersection is trivial. That's what a Malnormal collection means. Or you can just take, I mean, this is still non-trivial when you just have a single subgroup. Actually, you can reduce the multi-case to the case of one by some combination trick, but then, so there exists finite index subgroups. Oh, I forgot to say that if you have a hyperbolic group and you have a quasi-convex subgroup, then the quasi-convex subgroup is also hyperbolic, and in fact, if G is virtually special, then the subgroup will be also virtually special. So each of these guys is a virtually special quasi-convex subgroup, and so there's, I'll say P prime, normal subgroup of P, or well, I mean a normal collection, that means there's P1 prime, which is normal, and P1, etc. find index. And so for any double prime, a normal collection inside of P, where P double prime is contained inside of P prime. Again, I mean collection P1 through Pn, which are normal in each of the PIs, and so that P, Pi mod Pi double prime is virtually special hyperbolic. Then if I take G and I quotient out by the normal subgroup generated by P double prime, this is virtually special hyperbolic.
It says that P double primes are also finite index.
The P, no, they don't have to be, yeah. I mean, if they were finite index, then I wouldn't have to say here virtually special hyperbolic. I would just say finite. Yeah, so that's a strengthening of Wise's theorem, actually.
I'm just having a hard time reading.
Oh.
So it's this finite index subgroups P primes.
P1 prime through Pn prime,
Finite index.
which are finite index in each, these are all finite index subgroups
Okay. Right.
of each of those.
You just wrote
And
finite.
P double prime, what's it?
I just wrote finite index twice. That's what confused me.
These guys are finite index in these. P1 prime is finite index of P1. Pn prime is finite index in Pn.
Fine.
There's an adjective modifying that noun, I guess.
Finite index is written twice. It's fine.
Oh. Oh, I see. Oh, okay. Thanks. Yeah. That's a good point.
I thought I was referring to the next one.
Yeah, thanks. I see. Yeah, then for any P double prime, which are, oh, yeah, normal in P and contained inside of the P primes, then, so that those guys are virtually special. So, for example, again, you can take a free root free, say, in X and Y, and you take any random word in X and Y, like X, Y, X to the minus 2, Y inverse or something, okay? Now, if I take the one relator group where I make this a relation, you get one of the famous Baum-Slot-Saltar groups. It's not hyperbolic or anything. But what is this theorem saying? It's saying that if there's some, so this is our P, this is say P1 is this subgroup generated this. This is a Malnormal quasi-convex subgroup. If I take a large enough power of this, so there's some n, so that if I take xy with the relator xy, x to the minus 2, y to the inverse, to the power of n times any other number is virtually special. Now, the group theorists are aware that one of Wise's sort of pet projects since he was a grad student and was
just a notational question. So that's the normal closure of all the P.
Yeah, that's the normal closure. Yeah, so double brackets means normal.
The normal closure, but
of all the different subgroups, all the different elements in P double prime. Yeah, so here you have a single subgroup, the normal closure. So you take the finite index subgroup is the subgroup generated by, so P1 prime is the subgroup generated by this element to the n. And then any further subgroup of that, well, it'll still be normal in P1 because it's cyclic, so that quotient will be virtually special. So the point is that this is a one-related group with torsion, and Wise was working on this problem for many years for the problem of Baumslog. It says one-related groups with torsion are residually finite. So you can see that this is a special case of Baumslog's question, but it holds, well, it's a little weaker though because you have to have a multiple of some fixed power. So then Wise worked a lot harder and was able to prove the general Baumslog conjecture. So what he proves is that if you have a one-related group of torsion, first of all, it's a hyperbolic group, delta hyperbolic for some delta. Second of all, it has a quasi-convex hierarchy, not necessarily a Malnormal quasi-convex hierarchy, but just a quasi-convex hierarchy. Now, the way that this theorem comes into the proof of the general statement, if you have a group with a quasi-convex hierarchy, that it's virtually special. To get rid of the malnormality, the idea is that you take a splitting subgroup with an amalgamated product of virtually special groups, and it's quasi-convex, and you do an iterated sort of quotienting using this Malnormal special quotient theorem, where these p-double primes are finite index, and you decrease the complexity of the subgroup from being quasi-convex with a certain complexity called the height. You do what we call height reduction, and until you get down to a subgroup which is height 0 and therefore is malnormal. And then you can apply the inductive argument of Hsu, Agol, and Wise. So, and that includes in this one-relator kind of case that even though he gets a special case of this Baumslog conjecture, proving the general version is sort of this complicated inductive argument. And I think I'm about out of time, but I guess maybe can I just say a couple words about the proofs of these theorems? I think I started a minute or two late, so. But anyways, so we have new proofs then of this Hsu-Wise theorem and of this Malnormal special quotient theorem. There's features that are sort of in common to both of them, which I think from our approach is a little more apparent than if you look at Dani Wise's approach. That the idea is that well, when you have a cube complex A and B, you want to get you can take a cube complex and you can do various operations on them to create other walls, and then the idea is to create enough walls on both sides so that the cube complexes induced on C match up. And so the idea is that you take the cube complex of B, these hyperplanes define what are called walls in the subgroup in B, and they're induced walls on C. And then you extend these walls over to A using some properties of special cube complexes, namely there's canonical retracts. And then you can arrange it so that the walls on B that induce on C match up with some walls that you produce over on A using the special properties, and vice versa until the induced walls on C all match up, and then you can just sort of glue the induced cube complexes together along C. So I sort of have a slightly different way of doing this than the way that Hsu and Wise do it, which is slightly more canonical. When you have walls associated with quasi-convex subgroups, there's a way of producing the cube complexes that are sort of minimal and a little more canonical than the way that it's produced by Sagiev. The Malnormal special quotient theorem is a similar kind of thing, where you want to produce walls in this quotient group, and you do it in a similar way. You use certain combination theorems where you take a wall in the virtually special group and you add in you combine it with some subgroups of these PIs in such a way that you get a wall that passes down to the quotient. And we work sort of equivariantly to find Hsu cover in a similar way to Wise. But the point is that we sort of produce the walls before before doing the killing. Sort of Wise does it sort of simultaneously or after sort of killing these, quotienting out these subgroups. But we sort of produce them before, get a nice hierarchy that then passes down to the quotient. And you see that it passes down using the techniques of relatively hyperbolic gain filling developed by Groves and Manning. So that's sort of a summary. Whereas in Wise's results, he uses this cubical small cancellation theory that he develops in his paper. So I think our approach is sort of more apparent where the hyperbolicity comes in to the arguments, sort of where the cube complexes are not as essential for seeing that certain things survive under Dane filling, certain properties survive under Dane fill, or under these quotienting process, versus in Wise's theory where it's the cube complexes are more important in his theory, but I think they're not, maybe a little misleading if you're just working with delta hyperbolic groups. Of course, his cubical small cancellation theory works in slightly greater generality than what we're in the context I've been talking about today. But anyway, sorry, I'll stop there.
Are there any questions for you?
Yeah, I'll
Where do the Kahn-Markovich surfaces fit into the theory?
Right, so so the theorem, I guess, that I raised earlier, it says that if you have a cubulated hyperbolic group, then it's virtually special. So Segui's main theorem from his thesis associates to an immersed pi-injected surface in a three-manifold an action on a cube complex, Katsuo cube complex. And with enough of these Kahn-Markovich surfaces, you actually can show that action is proper and co-compact. So closed hyperbolic three-manifold groups are cubulated. That was proved after Kahn-Markovich's work by Bergeron and Wise, but using Segui's theorem. And then so then my theorem says that there's a fine-tuning covering space, that complex is special. You know, special group, it's actually has positive first Betty number. In particular, it's the three-manifold will be Hawken. But all those surfaces will be embedded. If the hyperplanes are embedded, then that corresponds to the surfaces being embedded. So there's a fine-tuning cover where all the surfaces become embedded. And so, so the three-manifold is virtually Hawken.
So the Kahn-Markovich surfaces, are they necessary in the theory or not?
Well, if you had some other way to cubulate three manifolds, then that would suffice. But yeah, I actually spent a while trying to cubulate three manifolds, you know, before Kahn-Markovich's work, using sort of other ideas, but nothing worked out. But yeah, all you need is the cube complex action. In the case of a closed three manifold, then in fact that Segui's theorem implies that there exists some codimension 1 surfaces in there that are immersed. If you have an action on a cube complex for a closed three manifold, an action on a cube complex is essentially equivalent to having some immersed pi1 injective surfaces. But we're going from the other direction.
Which small cancellation groups are virtually special?
Right. So Olivier and Wise proved that I think it's C'16, C'6 or C'16. I don't. Yeah, I can never keep the small cancellation notation straight, but I think it's C'16 groups are. I think they proved those are cubulated. They're delta hyperbolic, and I think. And did I get that right? The group theories, and they're cubulated, so they're virtually special. And yeah, in the same paper. Oh, sorry. Wise proved C'16 groups are cubulated. Then Olivier Wise proved that if you take a random hyperbolic group in the sense of Gromov at density 1/12, then it'll be C'16 and therefore cubulated. So these are groups that have lots and lots of relators, but they're lots and lots of very long relators, but not too many. So you still get a hyperbolic group, and it's C'16, and therefore cubulated.
Are there any other questions for you? Thank you.